Hello, everybody. So it's good morning, good afternoon, good evening for some of you. Super excited. I can't tell you how excited I am to be introducing our keynote speaker today, Dr. Juan Flores Preciado with SpaceX. So those of you that know me know I'm a huge space enthusiast, and to be able to bring both these worlds, right? Lubrication and tribology and space together is a huge personal thrill for me. So, Dr. Juan, thank you so much for sharing with us and joining us. And the floor is now yours.
Hey, hello, guys. Yeah, thank you for the invitation. Definitely, it's a pleasure to give a presentation today here with you. I'm just gonna go ahead, I guess, and share my screen, and I hope you can hear me well. John, you see this?
You're good to go.
Awesome, perfect.
Looking good, Juan. Thank you.
Awesome. Well, thanks again for the invitation. As he mentioned before, my name is Juan Flores, and I work in the science engineering department at SpaceX. And today's presentation is going to be about the space and harsh environment lubrication. That little thing that you can see over there was painted by my niece when she was 8 years old. So she also loves rockets and planets and stuff like that. So it was pretty nice to put in my presentation. Yeah. So time ago when I was doing my PhD, my roommate, he's a Greek guy. He used to say like, hey, every single word in science is usually coming from a Greek, has a Greek root, right? But in this case, lubrication is actually a Latin name. It was used in the around 1620s, and I really like the definition, which is like make a slippery or smooth, which is basically what we try to do sometimes, not always, but sometimes. Especially by the application of an oil, like in the days. Now we also use oil, but a little more sophisticated. Coming from the Latin lubricatus, or lubricare, to make slippery or smooth. So pretty much what we do right now, right? Even though tribology was basically established in the 1960s by a professor at the University of Leeds, it seems like ever since 1620s, people have an idea about lubrication. Cool. So this is the outline. Something that I want to do today for this presentation is not exactly to talk about a very specific area of research or debating a very specific failure or topic, but this is like a more general idea of what lubrication means for the space industry, not only for us going to space, but also in terms of our ground equipment, because we also have a lot of ground support equipment. And it's, as you may know, most of the launch sites in the United States are located in areas that are close to the coast. They tend to be corrosive.
Hey, Juan.
Yeah.
Could you check your audio? I'm terribly sorry. It's a little choppy.
Oh, okay. 1 second. I'm using my microphone, so I wonder if maybe I should use the computer audio.
Yeah, it sounded earlier. It sounded better earlier before you started.
Is that right? Okay. Let me. It's not getting any better.
That's better.
It's better now.
That's better.
Okay, cool.
Yeah.
Just let me know, and then
Right.
I can check. Probably I can just go ahead and go directly to my computer audio. Cool. Okay. Yeah. Let me know if you have any issues.
No, when you go to full screen,
Uh-huh.
when you go to full screen, it cuts out. So maybe just let's do that.
Is that okay?
No, something switched. We're sorry, everybody. This is technical difficulties, but we'll get through it.
Okay.
So maybe reset back to your mic.
Can you hear me now?
It's still choppy.
Oh, okay. Let's see what we can do. I'm gonna try to see if I can use my computer audio.
Okay, that's good.
Can you hear me? I'm using the computer audio now.
Yes. Yeah, we're good.
Okay. Excellent. Let's go to presentation and let me know what happened.
Okay.
What about now?
Sounds good.
Awesome. Perfect. Okay. So it seems that there's an issue with my headphones. Okay. So I'm gonna use the computer audio. Let me know if you have
No, Juan. Yeah. It's when you share the. So reset your audio now again. Sorry, and maybe just present without doing the full screen.
Is that any better now?
No, you have to reset your audio again. It's when you go to full screen that it happens.
That's very interesting.
I think I'm an IT guy, but we're gonna get through this, everybody. This is too important not to get it right.
What about now?
Okay, you sound good, and I would recommend that you don't go to full screen. You just do it.
Okay. Yeah. So I'm gonna go full screen then. Is that still okay?
Yes.
Okay, good. Awesome. Yeah, let me know if there is any problem, then we can try again. Cool. Okay, so yeah, this is a little bit about the outline. So once again, I'm just gonna try to be as general as possible, so you guys have an idea about our different environments for the space industry and the space companies. The type of lubricants that we normally use in the space, which is we don't really have a lot of options, which is good indeed. Some of the additives that are added to liquids and solid lubricants to improve some specific properties. Also going to talk about space lubricant failure, just a couple of them to give you an idea about the importance of calculating and planning your lubrication systems when you send multi-billion-dollar spacecraft to space. And also lubrication testing, just a very brief definition of the testing that we normally perform, and what is the future of space tribology now that we want to go to Mars, we want to go to the moon, and obviously Q&A. Sounds still okay? Cool.
Yes.
Okay, awesome, perfect. And then again, as part of the outline, space, as I mentioned before, is not only, the rocket, it's not only the satellite, but it's like an agglomeration of different systems, terrestrial system, and also, I love this word, extraterrestrial system, right? Which is the rocket, the ground communication, the antennas. In this case, we do have now an International Space Station that is almost 30 years old. The International Space Station has plenty of mechanisms that are moving, rotating, actuating, so it requires a lot of lubricated systems. The deployment mechanisms, every time we send a spacecraft to Jupiter, to the moon, to Mars, Even though there are not a lot of rotating components or moving devices, the activation mechanism to open the antennas, to open the solar panels, to move the reaction wheels are very important and are usually a single point of failure. Obviously, the rocket engine as well, you have the shaft, you have bulbs, you have different actuation systems. And although the majority of the components inside the rocket engines are sealed, so they don't really see the vacuum of space because we do a very good job sealing those surfaces, it's also important to think about any potential failure of the sealant. So therefore, we have to protect the lubricant system as well. And another one that is obviously almost 100% of the time hermetically sealed is the reaction wheel. The reaction wheel basically produces momentum by rotating 1,000, 3,000, 4,000 RPMs to maintain the position of the satellites most of the time. Something that I want you guys to keep in mind is that in space as well, every time we are working with a lubrication system or a lubricated system, or we are designing a lubricating system, for us it's very important to look at the environment, right? What is going to be the environment for my specific mechanism? Because most of the time, before we send something to space, we have to do a lot of testing here. We have to do a lot of ground testing. We have to be sure that everything is going to work perfectly. So obviously the environment in planet Earth is not the same as the environment in space. And we cannot always mimic the space environment in the lab because it's just not cost effective. So we have to take that into consideration, right? The testing environment is going to be different than the actual and the final application environment. And especially now that we want to go to Mars, right? We first have to understand how's the environment there. What is the pressure? What are the reactive species? What are the different contaminants, dust that may be around Mars? Also the same whenever we go to the moon, right? Now is the plan to go to the moon and to go there to stay, right? Probably, the gravitational forces that are slightly different, and that will impact your loading calculation and your contact pressure conditions. So again, that's something that we have to take into consideration. And also something that we normally have here in Earth is reactive species, right? Most of the time, oxygen, hydrogen, water will react with your lubricant or your greases and produce a tribofilm. And sometimes it's actually good. It's a positive effect on the lubrication system. In our case, when we go to space, there is no such a thing, right? There's no oxygen. We cannot form an oxide layer to protect the surfaces. It's just there are some other reactive species that we are going to discuss a little bit later, but they are not the same in a terrestrial or extraterrestrial environment. So that's something that we always have to keep in mind, right? Before you design a lubrication system that is going to space, you have to know as much as possible about that environment. And also something that is very important for us in the space industry is some lubricants can improve the low carrying capability of a system of material, right? Sometimes we don't want to fly something that is super heavy like stainless steel or steel. Therefore, we use aluminum. Aluminum doesn't really have the best low carrying capabilities, right? You're going to have deformation very rapidly if the load or the pressure is very high. But some of the lubricants like dry film lubricants, because it has such a low shear, it may improve the low carrying capabilities of your base material. So that's something to keep in mind. The lubrication is not only about making a surface slippery and reduce torque for activation, but it may also improve the surface properties of your material. Cool. And then I call this a road to nowhere, right? Because we don't want to have a lot of wear when we go to space. And this is a little bit of a timeline, right? From the beginning of the space race until now, right? So at the beginning, in the 1950s, the 1960s, the missions were relatively short, right? A few hours, a few days only. So they were able to use even liquid lubricants before the low vapor pressure or the vacuum in space starts evaporating the greases or the oils. And then after the 60s, when we go to the moon, then the missions were a little bit longer, right? Months. Or now that we have satellites in LEO or GEO orbits, it has to be 5 to 10 years. So the mechanisms are a little bit more complex. Therefore, the durability of the endurance of your greases and lubricants and solid lubricants are very, very important as well. The International Space Station. Now we're going to go to Mars. Then we are planning to build a space station around Mars, another space station around the moon. So we don't really have a lot of information about what is the effect of ultra high vacuum in deep space on the stability of our greases, even the best greases. And also, we don't really have a lot of information about the radiation damage. What happened with radiation when the radiation interacts with the greases as well. So that's something that is still kind of work in progress. What is a harsh environment, right? I really like this definition from Pacific Northwest National Lab. They basically say, when we are placing a system in an extreme environment, some of the materials behave just in an unexpected way, right? That is unpredictable. And then understanding the forces that may affect the material behavior in this kind of environments is very important for reliability and also to better calculate the life of your systems. And again, as I mentioned before, for a space industry, we have to take into consideration not only space environment, but also ground environment, right? So some of our facilities, as I mentioned before to you, are located in California. This is a very nice map. This is a corrosivity map for the United States. So our headquarters are located around this area in Los Angeles. So you can see red. So it's highly corrosive environment. Our launch pad is located in the Kennedy Space Center. It's also red. So we're basically located around the areas that are just red. Therefore, they are highly corrosive. And you can see this beautiful picture of the space shuttle when it's like a natural salt spray chamber around the shuttle, right? There is so much salt, there is so much fog that we have to take that into consideration whenever we do our greases selections, right? So, and also something that is really important for us is oxygen and fuel compatibility, right? Because we use methane, we use RP1, we use different type of fuels, but also we use a lot of liquid and cryogenic liquid oxygen, right? Oxygen is highly reactive and highly flammable. Therefore, we have to select a lubrication system that does not react with the oxygen, is not susceptible to oxidation, and also is compatible with the fuel that we use, so we do not contaminate the fuel for our rockets. And also something that is important for us is the cryogenic condition. We have to deal with liquid fuel, like liquid RP1. RP1 is nothing but rocket propellant. And liquid oxygen, which is also a cryogenic condition, oxidant. And also right now for the Starship, we use liquid methane. Therefore, because we are dealing with extremely low temperature, we have to have a grease, we have to have oils that have relatively good viscosity index, right? They can work well at cryogenic temperatures, and also at very high temperatures. So in a relatively wide range of temperature. The same happening in space. Sometimes when you go to space and you launch a satellite, the satellite is going to get hot when it's facing the sun, and then it's going to get cold when it's not facing the sun. So there are these kind of like thermal cycles taking place even on a flying satellite. So this kind of information is very important for me as a surface engineer, lubrication engineer working for space industry, to keep in mind the temperature changes, and also how it's just going to go colder and colder and colder as you go to deep space as well. And also we deal with highly pressurized system. So I wasn't really familiar with this kind of system. So that's a learning curve for me as well in terms of safety and security. And now that we know a little bit more about the harsh environment in a terrestrial system, what happens as soon as we leave air? Well, the first thing that you will notice is vacuum, right? It's just vacuum over there. It's very high vacuum, 10 to the minus 6 or 8 torr. LEO means low Earth orbit. So yeah, this here is around 10 to the minus 6 torr, and then as you keep like traveling all the way to the moon, it's ultra high vacuum, which is maybe all the way to 10 to the minus 12 torr. So water will evaporate immediately, blood will evaporate immediately. That's why we have to use these super fancy spacesuits. Something else that we have to take into consideration that we don't care here in Earth, right? We don't care about high vacuum. Oh well, sometimes we do. Is you are working on a vacuum system. Thermal cyclic UV radiation is very different over there, right? Because right here we have the ozone layer that will protect us against very strong UV radiation. Over there, there's no such a thing. There is nothing shielding us from the really high radiation coming from the sun. And also remember, most of the time radiation can produce cancer on your cells because it's so reactive that it starts breaking down your DNA. The same happens with radiation in space. It's so strong that it may start breaking down the molecules of your greases. Therefore, we need to select greases that are highly resistant to radiation damage as well. And there is plenty of information there. You have Newton radiation, you have gamma radiation. There is really a lot of information in that area, and that is an area that I'm trying to explore right now. How much do we know about deep space radiation interaction with solid or liquid lubricants? So again, trying to describe the harsh environment in space. Cool. Now we're gonna speak a little bit about the type of lubricants that we can use in the space. Thanks God there are not many options, so that's good and bad. But anyways, this is a European Union astronaut that is using. You see this little gun over here. This is like a space gun for lubrication, to replenish lubrication. They also have a coffee maker that can work under low gravity and high vacuum. This is super awesome. Anyway, so as I mentioned before, sometimes we can use solid lubricants that I really truly love and liquid lubricants. And there are significant differences between both of them, right? Like volatility, endurance or durability, the temperature ranges where they actually operate, the friction and torque noise. It's definitely much better for the liquid lubricants compared to the solid lubricants. They have basically very different applications. Sometimes you don't want to use a solid lubricants is your speed is very high, right? Unless you are formulating your solid lubricant. When I say solid lubricant, it's like molybdenum, graphite, PTFE, even something that we normally use in our daily life. And also, something that is important for us is can I prepare or design an accelerated test, right? Can I learn about that particular lubrication system in a short period of time, or I have to run it like for 11.5 years? So sometimes it's not that easy to accelerate the testing for solid lubricants, and it's a relatively it's the other way. Sometimes it's easy to accelerate testing on solid lubricant. It's more difficult on liquid lubrication because there is some chemical degradation process that is really hard to simulate. And also, the greases that we can use for a space environment normally are not sensitive to air or moisture. It is not the same for solid lubricants. Some solid lubricants are highly sensitive to the availability of moisture or water or hydrogen or carbon. So that's something to consider. And also substrate sensitivity. Sometimes additives from the greases can chemically react with the base material and damage the base material. So that's something very important, and I'm sure that you guys are more familiar with lubrications. Sometimes it's something to take into consideration, right? What kind of material am I lubricating, and is this material iron, nickel, copper will chemically react with the greases? That's something very important for you to consider. So these are some examples of the different space lubricants that we use. We can use liquid lubrication, which are normally hydrocarbons and PFPEs. And there is a new generation of liquid lubricants that have very good, very low vapor pressure, which are called the silo hydrocarbons. In terms of the hydrocarbon, we normally, PAOs are really not the best because they don't have really good vacuum stability. But there is a new generation. It was developed in the late 90s, the multiply alkylated cycle pentanes, or MACs. These are really, really good synthetic hydrocarbons that are giving us really good results so far. There is some chemical reaction with iron-based alloys, but there is a way to protect the base material to avoid the reaction. Something that I want you to keep in mind is the new generation, the silo hydrocarbons. They have it's basically a silicon-based polymer. The PFPE are basically a fluorine-based polymer, whereas the MACs are basically a normal carbon-based hydrocarbon. So silicon, carbon, and fluorine. We're supposed to finish at 8:45, right?
Yeah, Juan, we can have a Q&A for the last 15 minutes. So
okay, perfect.
If you have another 10 minutes, that's fine. So we can make it 10 minutes.
Yeah, perfect. Awesome. Yeah. And then again, something else that we have to consider when we are working with this limited amount of options that we have for lubrication is like, what can I do to improve the properties of these particular lubricants, right? And we do something similar that we do for normal lubricants, like lithium-based greases, right? Which is adding some additives or reinforced particles in order to improve the properties of these lubricants. What properties do I want to improve? I want to improve low carrying capabilities. I want to improve thermal stability. I want to improve speed. I want to rotate my component faster. And I want to improve oxidation and corrosion, right? Now, for us in space, it's like, okay, good. You improve the low carrying capability of the lubricants, but will this affect the radiation resistance of the material, the atomic oxygen resistance of the material? What is going to happen is I'm going to take this particular grease all the way to deep space. So that's something that in my case, I have to take into consideration, right? And I'm just going to give you an example. This is a very nice study. Basically, what this group did in China is they exposed different greases that are used in space to different type of radiation, right? They're exposed to atomic oxygen. Really quickly, atomic oxygen, like for instance, what do you breathe? You breathe O2, right? You breathe gas oxygen. As you go to the upper atmosphere, you will have ozone, which is an O3. As you go to space, you have atomic oxygen, which is O1. It's a highly energetic, super fast molecule that is just jumping around space, impinging whatever is finding on its way. It's so energetic and it's so tiny that it can break down molecules that are exposed to atomic oxygen. And then protons that are usually closer to deep space, UV, and electron irradiation. So when they did that, they observed significant changes in the coefficient of friction due to the interaction of the greases components and the different radiation systems, right? In this case, they test PFPE with molybdenum sulfide and then PFPE with PTFE particles. So once again, okay, yeah, your grease is extremely fancy, it has a lot of chemicals, but guess what? The PTFE is not very resistant to atomic oxygen, right? So I'm reducing the quality of an expensive grease because I'm adding PTFE particles. It may be good under some application, but it's not good if it's exposed to radiation. So again, that's something that we have to take into consideration that we normally don't care when we are in a terrestrial environment. And then I'm pretty sure that maybe most of you guys are familiar with solid lubricants. The main point with solid lubricants are normally based on molybdenum sulfide, graphite, or PTFE. And the beauty of this material is they have very low shear strength, right? The molecular bond is usually covalent, so it's very strong. But between the molecules, it's just a van der Waals force. Therefore, you can easily shear this material, and because of this low shear, they have a very lubricious type of surface. So that's the main difference with the liquid lubricants. Is widely used right now, especially molybdenum sulfide. on some bearings, especially bearings that are like a mid to low rotation speed. And it's a beautiful, beautiful microstructure. It's a microns to nanometer thickness, and the life is highly predictable. You can predict the life very, very easily. There is a lot of information in this box, but the only thing that I want to make clear for you is that some solid lubricants are not always compatible with oxygen, right? So that's something that we have to take into consideration. How much load it can withstand, what is the friction and vacuum conditions, what is the minimum and maximum temperature, and then what is the oxygen compatibility, consider that we use oxygen in our rockets. So things that we probably don't care that much in the terrestrial environment, we do in the extraterrestrial environment. This is another clear example of what happens. Sometimes we can also dope our solid lubricant to increase some of the properties, right? Like for instance, this study that you can see right here, they use nickel on the molybdenum sulfide to improve the low carrying capabilities. But they also realize this is friction versus distance. They also realize that they increase the life of the molybdenum sulfide, right? The undope is the black one, the dope is the blue one. So they reduce friction a little bit, but also extend the life of the lubricant. So that's something very important for me, especially is I can remove or replenish the lubricant in space, right? So this is something that I'm currently doing, some kind of like benchmarking, literature review, see what is available in terms of space studies, and then I can go ahead and start designing my lubricated systems. Yeah, I can probably skip some of these things, and then just go ahead of a quick. This is a very nice lubrication failure that happened in the International Space Station. So International Space Station, as you know, have gigantic solar panels, right? So those solar panels are like sunflower. They have to follow the sun. And the way they do that is by adding some sensors to the solar panels and then using some kind of like low-speed bearing activation mechanism so they can follow the sun. Back in the late 90s, they observed that it was very difficult to move the solar panels. They were like, hey, why do I need so much torque to move them? And at some point, some of the astronauts literally have to do an extra vehicle activity. So they literally have to go there and have a look. And they realized that there was a significant damage on some of the areas that are some of the rotating components that are activating the solar panels. You see debris everywhere. You see wear on different contact surfaces. And they were like, oh, Houston, we have a problem. So it was so complicated that they have to take some samples, ship the samples back to Earth. The labs from NASA have to assess the damage, and they realized that there was the nitride layer from one of the surfaces where showed significant damage, and they thought that it was exposed to a very high contact pressure. And they basically simulate the same environment at NASA, and they realized that one of the rollers was slightly tipped and slightly tilted, and and therefore, because the surface area was significantly lower, it was a very high contact pressure. Because it was a very high contact pressure, then the nitride layer wasn't able to withstand that damage. Basically, what they did is they sent an astronaut, repair the process, reapply a new coating to the rollers, and they have to use a highly stable vacuum grease to repair this mechanism. So it was a huge effort because of a bad tribology design. That's another example of the Galileo mission. You can definitely Google it. It's a really nice example of what happened when you overtest in a terrestrial environment and then consume the life of your lubricated system. Then when you send the mission to space, guess what? It's over. You don't have a coating anymore because you remove the coating during the terrestrial testing. You can just Google it. It's really nice. Yep. And then, just super quickly for space lubrication, we use tribometer, we use component levels, and we have to do mechanism level as well because of, our customers ask us to do that. It's extremely, extremely expensive. Therefore, I try to do as much as possible in the tribometer to be sure that I pre-screen my greases really well. Well, maybe we can go ahead and go ahead to the Q&A sessions to compensate with for the technical issues.
That's fine, Juan. Amazing presentation. Thank you again for sharing all that. A great response, and you can't see obviously, but in the chat, there's a lot going on, and even we have Greg saying, I guess your niece
Thank you.
So thanks for that. And I know there's a few questions coming in. One of which is, do we need some type of analysis, to the components, right?
Yes, yeah, we do. Something that we notice, especially for some of the fancy lubricants, like the MACs or the PFPEs, they sometimes chemically react with some stainless steels. And they produce what we call the Lewis acid attack. So we normally have, every time we try a different grease with a different additive, we have to test for compatibility with the base material, and it's normally performed by a chemical analysis of the oil.
Got it. Do you foresee, because I know there's a lot of, there has to be maintenance in the ISS and all these different areas. Do they have, I don't want to say like an oil analysis lab, or do they have those type of testing capabilities in space? Do the tests work in micro zero?
Yeah. So one of the things that they do test torque, right? They do take current, right? Okay, how much current do I need to spin the wheel? How much current do I need to move the solar panels and all the moving components? Everything is most of the time connected to load or current sensors. And then if they see a spike or an issue there, then they have to proceed on some of the repairs mechanisms. They do have something that they call the positive injection process. So like a tiny piston that constantly inject more lubricant to specific areas. There's like a little pump, right? Oh, I'm running out of oil in this reaction wheel. They just basically start injecting, because there are many places where we still use liquid lubrication, right? But those places are usually hermetically sealed, so they don't see the vacuum of the space. But as far as I know, they don't do chemical analysis of greases. If there is an issue, they send it back to us, and then we do the analysis in house.
That's not so easy.
No. Yeah.
All right, we have a question from Kuba here. So when you refer to solid lubricants, are those mostly bonded coatings?
Mm-hmm.
And then there's a second part, you see it there? Okay.
Mm-hmm. Yeah. So is we're going to go, depending of the location, right? For terrestrial location, we can use even brush or spray that are heat cured to improve the adhesion. And for components that require more precision or better endurance, then we do a spattering because it's much more easy to control the thickness. Graphite is tricky, right? Molybdenum sulfide is really good under vacuum conditions because it doesn't like humidity. On the other hand, graphite needs humidity to work, right? So graphite is not the best lubricant for space application. And it's also conductive, so even short circuit systems.
That's just awesome. And then our friend Rich, who's got experience in working those environments. So Max. I think that it's cut off there.
So what is the beauty? The beauty of the MACs is that they are very good at taking additives. They are open for business. They are open for additives. The PFPEs, they don't really like it. It's very hard. It's very hard to change the formulas or add additives or to PFPEs. Whereas MAC, which are hydrocarbon, right, is a carbon family of lubricants. It's much more easy to play with the chemistry. But you are right. As far as I know, they don't have the an aromatic, but the silicon base do. I don't know if you are working on that particular chemistry, Richard.
I think the question is, do they show good radiation resistance, the MACs?
Oh, the MACs do, yes. Yeah.
And then Gary's asking about how you age the lubricants. with the various radiations?
Yeah, so we use radiation chambers. Like for atomic oxygen, we just basically use plasma to ionize oxygen, and then magnetic field to accelerate the oxygen. So it's like a vacuum chamber. For UV, there are UV lamps that you can buy on Amazon even, and the only difference is like instead of using, like for instance, whenever you do paints, you do UV testing, right? Right? Which are like basically lamps with a UV wavelength. The only thing that we do is we place it inside a vacuum chamber, so we can do UV and we can change the wavelengths and stuff like that. So yeah, it's really not that. I mean, for protons, electrons, or like a stronger radiation, we can do it. We have to send it to NASA or a national lab. Yeah.
Excellent. And then Greg's asking, how do you qualify lubricant for space use?
We are kicking off our tribology lab. We don't have a lot of equipment just yet. We're working with a lot of partners in universities. But yeah, because it all depends, right? If you're working with NASA will ask you you have to do a lot of testing, right? You have to do chemical compatibility with the base material test. You have to do tribometer, right? Pin on this, 4-volt testing to assess the maximum low current capabilities of the material. So the approval process is, yeah, it can be long. It can be long, but we rely on a lot of data provided by the suppliers, right? Some of the grid suppliers are pretty open to work with us and provide us with information. But yeah, we do some internally and we have to do some externally.
So I have this question, and you mentioned a little bit about extending the life and maybe somehow reality. I think you're using nickel, right, to extend the life.
Yeah.
Are there any plans as you're looking at long duration flights and occupying interplanetary to try to extend the life and realize?
Yeah. Especially for the dry-flame lubricants, it's very unpredictable. And it's a relatively simple molecule. It's just molybdenum sulfide. But if we want to increase the low current capacity, let's say from 90 KSI to 120 KSI, we have to dope it with something. We have to add particles that can withstand that additional contact pressure, right? Nickel is an option because it's very compatible with molybdenum sulfide. Titanium, tantalum is also compatible. And it's not only helping us to improve the low current capacity, but because it's harder, help us to increase the endurance of the life of the system. But also, a lot of people say, oh no, I'm doping, and they just mixed it, right? Mixing is not the same as doping. Doping is you remove one atom from the molecular structure and add a new one, right? Whereas mixing, you just blend things together and then see what happens. So yeah, and whenever we do mixing, the life is really no anything better. So yeah, in order to extend the life of some of the current compounds, yeah, I think we need some help from chemists and people that know how to play with all these little things. Although the current MACs or PFPEs, they're really good. They're really good actually. We have been using those since the 70s for the PFPEs and the 2000 for the MACs. So there is some good amount of data.
Excellent. And then we have a few more questions before the time is up. So Mouse is asking, what are the MACs versus PAOs?
The vapor pressure. MACs can withstand pressure of 10 to the minus 13 torrs, which is basically close to the moon pressure. It's an ultra high vacuum. PAOs at some point they start breaking down over a long period of time when they are exposed to vacuum. But I think there are people working on those, improving the life of the PAOs as well.
Excellent. And you mentioned before that you're open to some help and experts in some of that field. So this is a good platform, Juan, for you to. There's many experts attending here, so please network yourself and take note. And I think we have let's call it one last question from Larry. So do you have any type of filtration, right? Presumably the fluid lubricants that you change or replace, and what happens?
We don't really use huge mechanisms that require lubrication. So we don't really use like a large volumes of oil or lubricant. So we don't usually, for terrestrial equipment, we do. For our satellites or our rockets, we don't. Yeah.
That makes sense. Okay, and I think that's our time. There's loads of thank yous coming through. For myself personally, on behalf of all of the LRVS community, we truly appreciate you being our keynote, sharing this knowledge. It's totally awesome.
Yeah, it's nice. It's nice. Sometimes I do that also with the students. Right, I wanted to let them know that tribology would take us all the way to Mars or the moon, right? And it's how important it is to have, from the Latin lubricatus, right? To have a slippery surface, to save energy, to properly deploy mechanisms. It's like it's a really important topic for sure.
Yeah. Excellent. Well, thank you so much. And is there any way if people have questions, right? They're chatting in here. They can connect with you on the app. How else can they get a hold of you?
Yeah, definitely. You can find me online on LinkedIn as well. But yeah, I'm gonna read some of these questions, and then and if you guys are a tribology, so you have a lab or you are a chemist, do some testing and publish. Awesome. We read papers, we read university publications. They are extremely useful. Is you have the possibility to publish, to create white papers, to work on chapters, stuff like that, go ahead. We read them.
Excellent.
We read them. Yeah.
All right, we've got to leave now on. Thank you so much.
Thank you. Bye-bye. Have a good one.
See you soon. Bye.
See you. Take it easy. Bye.